Hello everyone, thanks for having us. Today I'm going to present you our work which is entitled Posture Prediction for Healthy Sitting using a Smart Chair. My presentation will have some introduction and I'll try to discuss about related works or proposed method. Here I will try to discuss about the data collection and give you some description about the data sets, the data processing phase and feature generation and selection, model development, data testing, and then I will try to discuss about the results of our work, and finally I will try to conclude and give some recommendations. Many people spend a large portion of their daily time sitting in an office chair or while driving car or attending a meeting. Senior people also spend a lot time sitting on a sofa at home, and the people with disabilities also spend a large portion of their time sitting on a wheelchair. Everyone needs to be more active, but at the same time, they also wanted to spend less time sitting down. As many researchers indicate, a person in the developed world who works primarily at a computer could reasonably sit for up to 15 hours a day. Older adults aged 65 and over also spend 10 hours or more each day sitting or lying down, making them the most sedentary population group. So all of this sitting comes with significant health costs, both from inactivity and from poor posture. And long periods of sitting have been linked to obesity, cardiovascular disease, and premature mortality. So poor sitting habits have been identified as a risk factor to musculoskeletal disorders and lower back pain, especially on the elderly, disabled people, and also office workers. And these musculoskeletal disorders can also cause chronic pain in the limbs, neck, and back. As we all know, in the current computerized world, even while involved in leisure or work activity, people tend to spend most of their days sitting at computer desks, and this can result in spinal pain and related problems. Therefore, a means to remind people about their sitting habits and provide recommendations to counterbalance this, such as physical exercise, is very important. And posture recognition for assisted postures have not received enough attention, as most workers focus on standing postures. Although most posture recognition systems focus on standing postures, there are some who try to study on sitting postures as well. For example, a research by Kazuhiro, who tried to use 64 sensors to classify 9 sitting postures used the support vector machine classifier, and they were able to get a classification accuracy of 98.9% when the sitting person was known, and when the person was not known, they were able to get 93.9 classification accuracy. Another study by Muslu also tried to employ 31 pressure sensors to identify sitting postures. And in their study, they try to collect 10 postures from a total of 50 participants, and they employ logistic regression classifier. And they were able to acquire a classification accuracy of 87%. Our proposed approach differs from the existing literatures in two main aspects. The first one is most of the above works focus their study on office workers, but our study, in addition to office workers, targets older people who spend much of their time at home. And the second one is we try to employ different algorithms for modeling our posture classifier using several pressure sensors, both as a seat and backrest of the chair. As I've said before, we use 32 by 32 pressure sensors. So when I proceed to our proposed method, in this study, pressure sensors were used for collecting the pressure distribution data from a sensor literature, So in order to collect seating pressure distribution data, the pressure math was built by Fondazione Bruno Kessler Research Institute, and the dataset was collected in a controlled lab setting into different forms, and controlled and realistic form. So in order to collect both the controlled and realistic datasets, we involved a total of 50 participants, 11 and 39 individuals for each respectively. In the controlled dataset collection, participants were told that what positions to hold, while in the realistic dataset, it was collected in a controlled lab environment, and we employ wizard of with technique, where participants perform activities to change the television channel by simply moving or changing their body position. For example, moving right corresponds to channel plus, and moving left corresponds to channel minus. So this is what the chair looks like after plated with pressure sensor mat. So a total of 1,980 and 4,875 data examples were collected for the controlled and realistic data sets respectively. And the controlled data set, as I have said before, was collected from 11 individuals who were told to hold a certain position for 15 seconds for every sitting posture, including empty and still positions. Data were recorded for the 32 sensor values in every half a second. So we have 30 snapshots of sensor values. Similarly, for the realistic data collection, we only used 5 sitting postures, excluding the empty posture class. From a total of 39 participants, 25 examples were recorded for each of the 5 postures, resulting in a total of 125 data examples for each individual or participant. The dataset was collected within an interval of 0.75 seconds at 5 different time stamps at T1, T2, T3, and T5. And the assumption in this data collection was that at T1, which is the first recurrent element, a participant might not have moved yet or might just be starting to move. And similarly, at time T5, participant might already be moving back to center. And we found at time T3, which is the third recurrent element, to be less noisy than the other timestamps, and good representative of the final posture, and hence easier to predict and useful for learning. Well, when I proceed to the data pre-processing phase, in the control dataset, the initial sensor data were in a .sense file format, and totally we were provided 11 individual records for 6 different sitting postures. And inside each individual file, there were 180 examples collected for each of the 6 sitting postures, and a total of 1,800 data examples were able to be extracted. After we extracted all of the initial features, we then continued to read the sensor values from each individual for each posture and put them into an S list, which we then mapped it into an 8x8 matrix for ease of manipulation. And finally, we put together all the sensor values of each individual into a single separated value file, which is CSV file. And similarly, in the realistic dataset, we were able to extract around 5,000 data examples from 39 participants, and we were able to extract initially 80 features from the raw data. But since 15 of the features were not necessary for our study, we removed them. And finally, after we extracted all of the initial features, we then continued to read the sensor values from each individual in a similar way that we did with the control dataset, and we mapped it into an 8x8 matrix for ease of manipulation. And finally, we merged all individual files into a single separated value file, which is a CSV file. So when we proceed to the feature generation and selection phase, In addition to the initial 64 sensor features that we extracted previously, we generated other features that will better describe our dataset and contribute to improve the classification accuracy. Since the pressure distribution of sensors on the chair has a great impact, we generate 4 other features by calculating the center of mass of the 32 sensors of the seat as well as the 32 sensors of the back. We then calculated the center of mass for both the seat and back sensors separately. We also extracted other features for each of the seat and back sensors, dividing the given sensors into 4 quadrants and for each. As you can see here, we try to generate a new feature by just dividing the sensor features into 4 different each. And a similar way in this table, we try to divide 32 by 32 pressure sensors into 4 different quadrants, and we were able to get additional 4 quadrant features. So when we come to the model development phase, the study is conducted using both the controlled and realistic datasets separately. In both cases, we have conducted various experiments using different combinations, such as using normalized or non-normalized datasets, using full sensor features, using selected features, using selected features with a portion of class labels for all of the 5 machine learning algorithms. And all the models are evaluated using the coupled cross-validation technique, and we also use the sklearn and TensorFlow libraries in our study. As can be seen in this table, we develop a model for 5 different classifiers, which were trained with top selected feature sets on the normalized control dataset. We train our model with a total of 1,800 data examples, where 1,620 were used for training and the rest were used for testing. As can be seen here, the deep neural network algorithm scores superior performance compared to the other methods, be it for the full class labels or a portion of them. Similarly, in this table, we can see this table shows us the classification accuracy of a model developed by the normalized realistic dataset using the recurrent element by employing the different class label categories for all the 5 classifiers. And here, as you can see, the random forest algorithm performed in all of the cases compared to the other classifiers. So when it comes to the results of our study, we totally conduct 8 experiments using the control datasets, while we conduct 6 different experiments using the realistic datasets for all the 5 classifiers. From all the experiments, the one we did using the deep neural network algorithm with normalized datasets and 4 class labels scored the highest result with 98% prediction accuracy. Among the 5 classifiers, the deep neural network algorithm, Gaussian Bayes, and random forest scored the highest performance in most of our experiments. But although most of the models trained on the control dataset were able to classify most of the sitting postures, it was also difficult to easily predict the back posture. And the main reason for this might be the usage of only the C sensors in the data collection, which resulted in the incomplete representation of back posture. The study using the realistic dataset, the highest score was recorded by the random forest algorithm with an accuracy score of 97%. From a model developed using the third recurrent element, using only the left and right class labels. This shows the random forest algorithm using a model developed by random forest algorithm using only the third recurrent element for the left and right postures. As we have seen in our experimentations, the model's performance improved when we used varying lengths of class labels and different portions of the time frame dataset. The reason for not correctly classifying the full postures might be due to the nature of the dataset, as well as the participants' motionless character. So, classification performance variations between these two categories of datasets, the control and rats datasets, attributed by it might be a number of class labels used, the data collection methods that we employ, differences in the data set size, and also individual setting habits. So when we proceed to the main goal of this study was to build a predictive model which can classify the sitting posture of a person and enable individuals to monitor their sitting habits for healthy living. For this purpose, we have conducted experimentations to build predictive models using both the control and rats datasets. And as a result, the model that we built using control dataset was able to classify six different sitting postures with an accuracy score of 93% using the deep neural network algorithm. And when we use only four of sitting postures, the deep neural network algorithm were able to perform a classification accuracy of 98%, better than the using full class labels. Using the RADSIC dataset, our predictive model was able to classify 5 sitting postures, and we were able to acquire 77% classification accuracy using third recurrent element for all of the 5 postures. But we were able to get a classification accuracy of 97% while we use only the left and the right class labels using the third recurrent element. So in this study, we used only a dataset collected within a controlled environment. We employ a limited number of participants and identified only 6 sitting postures. So for future work, our method can be extended by collecting real-world datasets, employing increased number of participants and also sitting postures. Different seating activities can also be considered towards developing a full system that can work with variety of chart types and also environments. So this is all about my presentation of our work. Thank you very much.